This will be section 1.2. Where we're going to start looking at patterns, but first I'm going to do a problem from section 1.1. Hopefully you can see that E is going to be the greater series because each term in E is larger by 1 than the corresponding term in O. So the issue is, how many terms are there? Well, to do that, I'm going to look at a simpler case. I'm just going to break these. And I saw you that in each of these, I have 4 terms. They're each also increasing by 2. So I'm thinking there's some relation there between the number of terms and that 2. And if I go, hey, 8 divided by 2 is 4. That gives me the 4 terms. Think about it. If I went to the next term, it would be 10. And 10 divided by 2 is 5, which would be 5 terms. So I think I'm onto something. I'm going to use it. I'm going to go to 98 divided by 2 gives me 49 terms in that series or sequence. And so E must be greater by 49 because each term is 1 more than the term in O. So that was using some reasoning from the last section where I looked at a simpler case and then I looked for patterns. Okay, we're going to look at patterns, different types of reasoning. We will explore this a lot more in a lab, but for now, okay, here's a sequence. What do we think the color of the next block will be? Well, we're going red, blue, green, red, blue. You may think green, but you're wrong because it's purple. So the kind of reasoning we just did is called inductive reasoning. Here's our definition. Notice we looked at the pattern and it looked like green should come up. That was our conjecture, that green was going to be the next block, but it wasn't. We had a counterexample where the next block was purple, and so that contradicted the conjecture. And that's the thing with inductive reasoning, is one counterexample will blow the whole thing up. Now look at the next one. All squares are blue. So when I hit the next button, I will generate a square. In this case, it is blue. I can't animate this. This is a different kind of reasoning. This is deductive. And it has to do with this statement. This is called an axiom, which is taken to be true. And the word all. So if that's taken to be true, all squares are blue, then the next square has to be blue. So we're basing this on logic, where we had an established axiom that all squares were blue. And now we can use this to prove conjectures. And this really is how math works. It's an axiomatic system that uses logic to progress. Okay, we just put things in order, which we did with the red, blue, green blocks. We can make a sequence, and we're going to look at a few of them and their properties. An arithmetic sequence. Notice that each term increases by 3 to get the next term, and that's constant. So I'm thinking of actually doing 14 subtract 11 is 3. 11 subtract 8 is 3. I call these the first order differences. Well, I don't. Math does. So let's explore this deeper. I'm going to give an arithmetic sequence. The 3 dots, the ellipses mean it just continues on. But I'm going to add something to this because I'm going to kind of change it into a little bit of algebra. I'm going to add the step number. So my n values are going to be first step. My term is 1. Guess I don't want a comma there, sorry. Step 2, step 3, step 4, step 5, and so on. Well, I don't like this organization. So in the previous section, we talked about using tables. So I'm going to put this into a table where I have my step number and I have my term. Okay, I'm going to change colors. Now, I do this. I have my thinking is now organized a little better. And I see that my first order differences are all 4. So first order differences. They are constant. Okay, because each one is 4. That means in my formula for this sequence, I'm going to get a linear equation. That's the information that gives me. Linear equations, if you recall, y equals mx plus b. In this case, I'm changing this a little bit to like the term is m times n, the step number, plus b. And here's the information that my first order difference gave me. It's constant. It's linear. That means the rate of change between each term is 4. That means that my slope of my equation is 4. And if you recall slope, that's your m. So I'm going to finish this off and find the formula or the equation. Right now I am here. I'm inputting my step number. I'm getting back the term. So right now I know this is 4 times n plus b. Remember, this is, if I'm thinking y equals mx plus b, this was called the y-intercept. Well, for me to finish this, I'm going to go up and select, I'll just use this last one because I can see it, 5 and 17. So my term, I'm looking at this ordered pair, the term is 17. The step number is 5. I'm going to solve for B. Subtract 20, negative 3 is B. My formula, the step or the term, is 4 times the step number, subtract 3. And all of this flows from this, the first order differences. All that information it gave me, it was constant. I know it's linear. I know the slope is my first order difference. And from there, it was a matter of algebra to find my formula. I'm going to let you do this one and take a moment. So you may want to pause before I do this and try and figure this out. Okay, I hope it came back. I've got 4, so I'm going to do my n and my term. I'm going to build my table. 1, 2, 3, 4. I'm going to count my math sticks, so there's 4. I'm adding 3, I got 7. I'm adding 3, 10. I'm adding 3 each time on the end. My first order differences are always 3. I know that the term is 3 times n plus some constant. I'll pick the last one again. My term is 13, is 3 times 4, that's my n, my step number, plus b. Looks like in this case, b is 1. So my formula, I'll use t for term, is 3 times the step number plus 1. And the thing that got me there was looking at the first order differences. Now, I've got a table here, and I'm asking, is it an arithmetic sequence? Well, let me quickly do the first order differences. And the one thing I can say for certain, no, because not constant. There's not a constant growth rate, so I don't have a constant slope. So notice I introduced second order differences. Let's go down and look at those. First order. Now I'm going to do the second order differences. Meaning, I'm going to look at the difference here. Notice that the second order differences, whoa, they're constant. What that tells me is my sequence is not linear. It's not linear because these were not constant, so not linear. But when the second order differences are constant, your formula or equation is quadratic. That means there's an n squared in the formula. And in this case, it just happens to be n squared plus n, 2n, my bad. Read my notes wrong. Gives you the term. I'll let you figure out where that came from. Good practice. It's not easy. Let's finish this up. Geometric sequence. So we've done arithmetic, looked at quadratic a bit. Geometric, introduced this because of this word ratio. So if I look at successive terms, meaning 6 and 2, and I do 6 divided by 2, that's my ratio, I get 3. If I do 54 divided by 18, I get 3. 18 divided by 6 is 3. This tells us when the ratios are constant, I have a geometric series or sequence. Okay, look at this one. 16, 8, 4, 2, 1, 1/2, 1/4, dot, dot, dot. This is geometric, because if I look at successive terms, 8 over 16 is 1/2. 1 divided by 2, 1/2. 1/4 divided by 1/2. Well, if you remember fractions, that becomes 1/4 times the reciprocal. That's 2/4 is 1/2. So I guess what I can leave you with is, what's the next term here? What are the next 3 terms in this sequence? And that's the end of this. It's always the hardest part.